Reactions of aromatic molecules, electrophilic aromatic substitution, introduction. 6 key electrophilic aromatic substitution reactions. In electrophilic aromatic substitutions, CH bond is broken and a new CE bond, E being electrophilic atom, such as ClBrN, is formed. There are 6 key electrophilic aromatic substitution reactions in most introductory organic chemistry courses: chlorination, bromination, nitration, sulphonation, Friedel-Crafts alkylation, Friedel-Crafts acylation. Each of these reactions requires an acid catalyst to activate, so the relatively unreactive aromatic ring will attack it. Quick summary: electrophilic aromatic substitution, unlike alkynes, benzenes, other aromatic do not generally undergo additional reactions. Addition to electrophilics such as Cl2 tends to result in substitution instead. These reactions are greatly facilitated by addition of Lewis acid catalyst. Key reaction pattern in electrophilic aromatic substitution: benzene or other aromatic, and electrophile and Lewis acid catalyst. Electrophilic aromatic substitution product: key bonds formed C-E, key bonds broken C-H. Friedel-Crafts alkylation, Friedel-Crafts acylation. Electrophilic aromatic halogenation, halogenation of benzene. X2 FeFX3 HX. Bromination, chlorination, iodination. Halogenation of benzene. Benzene reacts with halogens in the presence of Lewis acid like FeCl3, FeBr3 to form airy halides. This reaction is termed as halogenation of benzene. The halogenation of benzene substitution reactions. Benzene reacts with chlorine or bromide in the presence of the catalyst, replacing one of the hydrogen atoms on the ring of the chlorine or bromide atom. The reaction happens at room temperature. The catalyst is either aluminum chloride or aluminum bromide if are reacting benzene with bromide or iron. Strictly speaking, iron is not a catalyst because it gets permanently changed during the reaction. It reacts with some of the chlorine or bromine to form iron 3 chloride, FeCl3, or iron 3 bromide, FeBr3. 2Fe plus 3Cl2 equals 2FeCl3. 2Fe plus 3Br2 gets 2FeBr3. These compounds act as catalysts and behave exactly like aluminum chloride, AlCl3, or aluminum bromide, AlBr3, in these reactions. The reactions with chlorine, the reactions between benzene and chlorine in the presence of either aluminum chloride or iron gives chlorobenzene. Or written more compactly, C6H6 plus Cl2 is C6H5Cl and HCl. The reaction of bromine. The reaction between benzene and bromine in presence of either aluminum bromide or iron gives bromobenzene. Addition reactions. C6H6 plus Br2 equals C6H5Br, HBr. Addition reactions. In the presence of ultraviolet light, but without a catalyst present, hot benzene will also undergo an additional reaction with chlorine and bromide. The ring delocalization is permanently broken, and chlorine and bromide atoms add onto each carbon atom. For example, if you bubble chlorine gas through a hot benzene exposed to UV light for an hour, you get 1 and 2 and 3 and 4 and 6 hexchlorocetrohexane. Bromine would behave similarly. The chlorines and hydrogens can stick up and down at random above and below the ring, as this leads to a number of geometric isomers. Although they aren't any carbon-carbon double bonds, the bonds are still locked and unable to rotate. One of these isomers was once commonly used as an insecticide known as BHC, HCH, and gamma-hexene. This is one of the chlorinated hydrocarbons which cause so much environmental harm. The halogenation of methylbenzene, substitution reactions. It is possible to get two quite different substitution reactions between methylbenzene and chlorine or bromide, depending on the conditions used. The chlorine or bromide can substitute into the ring into the methyl group. Substitution into the ring. Substitution in the ring happens in the presence of aluminum chloride or aluminum bromide if you are using bromine, or iron in the absence of UV light. The reaction happens at room temperature. This is exactly the same as the reaction with benzene, except that you have to worry about where the halogen atom attaches to the ring relative to the position of the methyl group. Methyl groups are 2 and 4 directing, which mean that the incoming group tends to go into the 2 and 4 position of the ring, assuming the methyl group is in the 1 position. In other words, the new group will attach to the ring next door to the metal group, or opposite. When chlorine substitution into the ring gives a mixture of 2-chloromethylbenzene and 4-chloromethylbenzene. With bromine, you will get equivalent bromine compounds. Substitution into the methyl group. If chlorine or bromine react with boiling methylbenzene in the absence of a catalyst but in the presence of UV light, substitution happens in the methyl group rather than the ring. For example, with chlorine, bromine would be similar. The organic product is chloromethylbenzene. The brackets in the name emphasize that the chlorine is part of the attached methyl group and isn't on the ring. one of the hydrogen atoms in the metal group has been replaced by chlorine atom. However, the reaction doesn't stop there, and all 3 hydrogens in the metal group can be replaced by chlorine atoms. That means that you could also get dichloromethylbenzene and trichloromethylbenzene as the other hydrogen atoms in the metal group are replaced one at a time. If you use enough chlorine, you'll eventually get dichloromethylbenzene, but any other proportions will always lead to a mixture of products. Addition reactions. I haven't been able to track down anything similar to the reaction between benzene and chlorine, in which 6 chlorine atoms add around the ring. That perhaps isn't surprising. Chlorine adds to benzene in the presence of ultraviolet light. With methylbenzene, under those conditions, you get substituted methyl group. That is energetically and easier because it doesn't involve breaking the delocalized electron system. Whether you would get an addition to the ring if you use large excess of chlorine and did the reaction for a long time, I don't know. Once all the hydrogens in the methyl group had been substituted, perhaps you might then get additional. The attacks on methylbenzene toluene by chlorine and bromide is facilitated by heat or light. Analysis of resulting products indicate the reaction occurs at the metal group rather than the aromatic ring. Furthermore, an excess of halogen leads to multiple substitutions. Mechanism. The mechanism of benzoic halogenation follows the same principles as halogenation of alkynes and acrylic halogenation of alkanes, proceeding through radical intermediates. When exposed to heat or light, the halogen molecule dissociates to individual atoms. One of these atoms abstract a benzyl hydrogen, resulting in formation of HX and a phenyl-methyl benzyl radical. The benzyl radical then reacts with another molecule of halogen, yielding a final product, a halomethyl benzyl halide, and releasing another halogen atom, which sustains the chain process. Order of operations is important in the synthesis of aromatic molecules. Sequence in which reactions are done on aromatic molecules can determine the product. Installing a meta-director will give the meta-product. AICI3 for Delcraft's acylation, to the meta-director. Then to AICI3 for Delcraft's alkalization gets your meta-product. Installing ortho-para-director, that will give ortho and para products. The AICI3 for Delcraft's alkalization, ortho-para-director, and the AICI3 for acylation gets your para product plus ortho. This becomes very important when trying to plan synthesis of aromatic molecules. Pyroxenine, pyroxyl, pyroxamine, pyroxyl phosphate. Pyroxamine, R equals CH2OH. Pyridoxal, R equals CHO. Pyridoxamic acid, R equals COOH. Pyridoxamine, R equals CH2NH2. Vitamin B4, adenine. Pteridine. A pteridine is a bisaccilic heterosaccilic system with 2 nitrogen atoms at positions 1 and 4 in ring A and 2 nitrogen atoms at positions 1 and 3 in ring B. Several compounds are identified as hits through pharmacological screenings of library pyridine-based compounds from fused pyrimidine-based drug discovery 2023. Pteridine is an aromatic organic compound composed of fused pyrimidine and pyrazine rings. Pteridines also constitute a group of heterosaccilic compounds containing a wide variety of substituents on its parent structure. Petrins and flavins are classes of substituted pyridines that have diverse biological roles. Chemical formula: C6H4N4. Molar mass: 132.126 gram. Melting point: 139.5 Celsius, 283.1 Fahrenheit, 412.6 Kelvin. Synthesis of pyridine from 4,5-diaminopyrimidine and glyoxyl. Function: Pteridine and TH metabolism have important and particular roles modulating neurotransmitters for development of neural system in the first and second decades of life. The deficiency of TH becomes apparent clinically with functional maturity downstream structures of these receptors. Compound name: Pteridine is also known as azanprine. Belongs to the class of organic compounds known as petridines and derivatives. These are prosaccilic aromatic compounds containing petridine moiety, which consists of pyrimidine fused to pyrazine ring form pyrimido brackets 4 and 5B pyrazine. 1-carbon 1C metabolism comprises a series of interlocking metabolic pathways that include methionine and folate cycles that are central to cellular function, providing 1C unit metal groups for synthesis of DNA, polyamines, amino acids, creatine, and phospholipids. 6. Folate mediated 1-carbon metabolism, source of the MAs substrate 5, methyl tetrahydrofolate, CH3THF, is a 1-carbon metabolic cycle whose carries folate. Folates encompass a set of molecules that contain a pteridine ring that can be oxidized or reduced. A para-aminobenzoic acid linkers that together with the pteridine ring may bind 1-carbon units and a variable length chain glutamate tail. Folic acid and oxidized folate form and a commonly used synthetic food additive is reduced at the double bond at nitrogen 8 to produce dihydrofolate DHF, while further reduction of the double bond at nitrogen 5 generates THF. The active coenzyme form both enzymatic steps are catalyzed by dihydrofolate reductants, DHFR. Once reduced to THF, nitrogen 5 and or nitrogen 10 may serve as acceptors of single carbon units. These carbons may be transferred at varying oxidation states as determined by their source and the enzyme catalyzing the reaction. 2. Cobalamin metabolism, structure, and intake. Once called nature's most beautiful cofactor, 3-CBL is at least nature's most chemically complex coenzyme. The focal point of CBL is the central cobalt atom, which can form between 4 and 6 bonds and can exist in redundant states. COB3 most oxidized, COB2 or COB1 element, which most reduced. There is a correlation between cobalt oxidation states and preferred number of chlorinated elements, whereby COB3 element often forms 6 bonds, COB2 element forms 5 bonds, and COB1 element forms 4 bonds. Of these, 4 cobalt bonds are always occupied by the nitrogen atoms of the planar core ring surrounding the cobalt. Cobalt may additionally bind a lower axial ligand and dimethylbenzylmidazole DMB, which attaches back to the core ring when bound. CBL is considered base on when not base off. Finally, the cobalt atom may also instead bind an upper axial ligand R group, which may consist of any number of compounds but whose human cofactor form include adenyl cobalamin ADO-CBL or methylcobalamin MECBL moieties, while glutenol cobalamin GNCBL and hydroxocobalamin OHCBL are also physiologically important, and cyanocobalamin CNCBL is common in pharmaceutical preparations. Xanthene alkaloids: caffeine, theobromine, theophylline. 3 natural alkaloids, derivatives of xanthene: caffeine, theophylline, theobromine, extracted from semi-synthetic uric acid, guanine, urea. 5 and 6. Dimethylbenzimidazole seems to be one area here which looks a lot like our caffeine and xanthine, but it is actually related to cocaine, as prepared by label methyl ester, methyl cocaine, or the N-methyl group of the tropane ring. Methyl cocaine later appears to be more commonly used and can be synthesized by treating norcocaine with CH3I and purifying the reaction mixture using semi-preparative HPLC. Caffeine will break down into 1-methylxanthine, and if it breaks down a little bit differently, it'll break down into 1,7-dimethylxanthine, which will break down into 1,7-dimethyluric acid. Caffeine can come in many forms, and just by slight changes, we get derivatives like caffeine C8H10N4O2 MW194. and caffeine G9, CHHD9N4O2, MW203. Theophylline, C7H8N4O2, MW180. Paraxanthine, C7H8N4O2, MW180. Paraxanthine D3, C7H5D3N4O2, MW183. Theobromine, C7H8N4O2, MW180. These are some vitamin B4 adenine, because when we see the synthesis of caffeine and theophylline by method Abramov was synthesized by Traub in 1900 year. Metallation of xanthine to form caffeine. In the tea and coffee plants, the main synthesis pathway of caffeine is a 4-step sequence consisting of 3 metallization reactions and 1 nuclease reaction using xanthine as a precursor. In bacteria, caffeine degradation occurs mainly through the pathways of N-dimethylation and C8 oxidation. How can you synthesize caffeine from xanthine? The results suggest the pathway of caffeine biosynthesis is as follows: xanthocene, 7-methylxanthocene, 7-methylxanthine, theobromine to caffeine. Did you take your vitamins today? Vitamin B, vitamin B6, vitamin B12, vitamin B deficient. When you're vitamin B deficient, it causes numerous health problems, disorganized thinking, ADHD, and what we sometimes consider mental illness, which is just vitamin D deficiency. Vitamin B is naturally produced within our body's methyl and folate cycles. When we metabolize vitamins, we get different vitamins: vitamin B12, B6, and B2. Cytosine, C4H5N3O, MW11.1. Uracil, C4H4N2O2, MW112.0868. Ephedrine, C10H15NO MW165.24. Benzoic acid, C6H5COOH MW122.12. Salicylic acid, HO, C6H4COHO MW138.12. Dihydroxybenzoic acid, C7H604 MW154.121. Cetacilic acid, C9H8O4 MW180.158. 3. Hydroxybenzoic acid, C7H6O3 MW138.12. 4. Hydroxybenzoic acid, C7H6O3 MW138.12. 3 and 4 hydroxybenzoic acid, C8H6O4 MW16613. Inidol, C8H7N MW117.151. Uric acid, C5H4N4O4 MW168.1103. Xanthene, C5H4N4O2 MW152.11. Hypoxythene, C5H4N4O MW136.11. Caffeine, C8H10N4O2 MW194.19. Tryptamine, C10H12N2 MW160.216. DMT, C6H4 brackets COOH3 brackets 2 MW188.27. Serotonin, C10H12N2O MW176.215. Psilocin, C12H16N20 MW204.27. Psilocybin, C12H17N2O4P MW284.25. Phenylethylamine, C8H11N MW121.18. Cathinone, C9H11NO MW149.19. Methacathinone, C10H13NO MW163.22. Ephedrine, C10H15NO MW165.24. Pseudoephedrine, C10H15NO MW165.2322. Amphetamine, C9H13N MW135.21. Methamphetamine, C10H15N MW149.2337. Propylhexidine, C10H21N MW155.28. MDA, C10H13NO2 MW179.22. MDMA, C11H15NO2 MW193.25. B12 is the sort of all of those compounds, all the alkaloids. Vitamins have all of the stimulants break down out of your vitamin B12 because of the folate and methyl cycles in our our metabolism, that we see vitamin B6 and B2 as well. It's just as simple as building hydrogen and oxygen to make water. The vitamins, they break down like ammonium oxide is Al2O3. So we put these elements together by synthesizing, and synthesis reaction is a reaction in which two simpler substances are combined to get a new compound. This is also called direct combination because the two simpler substances are directly getting combined without any decomposition or dissociation, and forms a new compound. 5 primary types of chemical reactions are combination reaction, decomposition reaction, displacement reaction, double displacement reaction, precipitation reaction, or the 3 steps of synthesis. The synthesis of any macromolecule proceeds in 3 stages: initiation, elongation, and termination. This is true for DNA replication as well. During initiation, DNA synthesis begins at a specific site called an origin of replication. Chemical synthesis involves mainly the growth of NPs in a liquid medium containing a variety of reactants. The sol-gel method is one such example for making quantum dots. Researchers also follow this method. If we were to take cold medicine, like Sudafed, and use an extraction method of acetone or methanol or toluene, the pseudoephedrine would break down, and we use a reduction of iodine and red phosphorus, and we will get methamphetamine. Just like if we were to take ephedrine or pseudoephedrine and mix it with lithium or natrium in liquid ammonia. This is called the Birch reduction for methamphetamine. If we were to take ephedrine or pseudoephedrine and mix it with hydrochloric acid, red phosphorus, we get methamphetamine as a Nagel method. If we take ephedrine or pseudoephedrine and mix it with prechloric acid, hydrogen gas, palladium, and barium sulfate, we get the Rosemont method for methamphetamine. What is natural pseudoephedrine? Pseudoephedrine is first known as a natural substance that occurs in shrubs of the ephedra genus, which grows worldwide. Almost all commercial pseudoephedrine, however, is produced by fermenting dextrose in the presence of benzaldehyde. After the yeast has begun fermenting dextrose, the benzaldehyde is added to the vats, and the environment, the yeast converts the ingredients to produce phentylacic carbonyl, LPAC, and LPAC is then chemically converted into ephedrine via reductive animation.